Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's Battery Tech webinar from Slurry to Cells, the journey of battery characterization, sponsored by Hioki USA and broadcast by Informa. I'm Michael Krieger, and I'll be your moderator today. Hopefully you can hear us now, and we have just a few announcements before we begin. The webinar is designed to be interactive. The dock of widgets at the bottom of your screen will allow you to learn about today's speakers, download resources, share this webinar, and participate in the Q&A session that takes place at the end. The slides will advance automatically throughout the event, and toward the end of the event, we will ask you to complete our survey. Please take a minute to fill this out before leaving us today, as your feedback gives us valuable information on how we can make these events better, like having the audio work all the time. And finally, if you're experiencing any technical problems, just click the help widget found at the bottom of your screen or type your issue into the Q&A area. We'll be glad to offer one-on-one assistance. Now onto our presentation. From Slurry to Cells, the journey of battery characterization. Discussing today's topic is Naomichi Mieri. He's the product marketing engineer at Hioki USA Corporation. And Isan Dalgic, he is the chief application engineer at Hioki USA Corporation as well. To learn about them, just visit the speakers widget. And once again, now, sorry for the problem. Thanks for joining us, and over to you.
Thank you, Michael. So today I'm going to introduce our latest studies and our solutions as well. But before that, I would like to introduce our company, since some of you are not familiar with Hioki. So established in 1935, Hioki Corporation has evolved into a global front runner by steadfastly providing testing and measurement instruments that excel in design, manufacture, sales, and service. Hioki USA, a pivotal player in electrical measurement innovation, plays a significant role in catering to the specific demands of the battery technology sector amidst the worldwide transition to more sustainable, efficient energy storage methods. Offering cutting-edge testing tools essential for research, development, and production phases, they emphasize precision, safety, and dependability. These tools are vital to improving battery efficiency, safety, and environmental friendliness, highlighting Hioki USA's crucial contribution to advancing green energy solutions. So, by the way, this is our headquarters in Japan. We design and manufacture our products over there. And the Hioki USA supports all people in the Americas from Dallas, Texas. So in today's presentation, I'm going to discuss slurry characterization, electrosheet characterization, and 3 case studies. So first, I will go over the current situation. So batteries are used in the diverse range of applications, from smartwatch through EV, and the battery designs are tailored to specific performance requirements and safety considerations. So specific energy density, specific power, cost, voltage, capacity, they are part of the requirements, and that they are optimized by application. And to achieve specific requirements, I can see 3 areas. So formulation, so material selection and the weight ratio are included. And after determining the formulation, we'll consider the production process. So mixing time, drying time, pressure for calendering, etc. They are decided in this process of development phase. And lastly, we manufacture battery cells. So they should be high quality, right? So uh, there are several techniques used for quality control, visual inspection, electrical evaluation, and mechanical evaluation. So this is a typical lithium-ion battery cell production process, which starts with slurry preparation, followed by electrode sheet fabrication. So um, through these processes, we'll produce cell, but to uh, to get desired battery cells, we uh, we should optimize the performance and performance by battery component battery component, and also we ensure the quality is right by battery component as well. So today I'm focusing on Slurry electrode sheets. So that I will introduce how Slurry is characterized today. So Slurry characterization. There are two key elements for slurry characteristics: rheological properties and the electrical properties. So rheological properties such as viscosity and the storage or loss modulus are characterized with a rheometer. On the other hand, electrical properties such as reactance resistance and the relaxation frequency are characterized with EIS, electrochemical impedance spectroscopy. And this graph is an example of a nice plot with EIS, and x-axis is resistance, and the y-axis is reactance. So materials in the slurry exhibit a distinctive frequency response, and by analyzing this nice plot, we can get more insight into slurry characteristics. So to do that, EEC is used, electrical equivalent circuit is used, but this analysis takes some time because frequency-dependent responses changed by material. So we developed the Slurry analytical system. This does impedance measurement and nice plots data analysis. So the meter, a slurry sample is put in a little vial, and we measure impedance with this meter. And then after that, the next plots are analyzed with a software application. The analysis takes within a minute. So based on material entry in the software, the software chooses the EECs, and we compare measured next plots with the ones from the models. So through curve fitting, we identify resistance and the CPE values in the EEC, and calculate the three slurry parameters indicators. So DCR is the total resistance of the slurry in the EEC, and our ratio is the percentage of resistive component of a conductive material in DCR. And the uniformity is the distribution of a relaxation by conductive materials. So these three indicators are calculated. So speaking of uniformity, we use unified RC circuit. So this image is the internal of the Slurry solution, and conducting materials are touched together, and the interface between materials, there are the RCEC is expected to be formed. But to simply analyze the uniformity, we use unified RC circuit. The impedance of this unified CPE, the impedance of the unified EC is calculated this equation, and if frequency response regarded as a single relaxation is observed, the shape of a Knight's plot becomes perfect semicircle. But if not, the plot would be distorted, and the CPE, meaning uniformity, comes to less than 1. So using our ratio and the uniformity values from 0 to 1, we can estimate the internal state of the slurry. So in this image, our ratio is on the horizontal axis, and the uniformity is on the vertical axis. Our ratio, from left to right, the electric pathways created are increased, and about uniformity from bottom to top, the material dispersion gets better. So next, about electrosheet characterization. So I'm going to introduce this characterization. Please take it over, please.
Thank you, Nao-san. Hi, everyone. My name is Isan Dalgic. My section of this presentation will be fairly brief. I want to talk about electrode resistance measurements, or measurements of the electrode sheets, the traditional methods, their limitations, and what the RM2610 Hioki's system brings to the table. So it's important to know, obviously, electrode sheet comprises of the composite layer and a current collector, but there's also the interface between the composite layer and current collector. So we can see the electrode sheet as at least 3 individual resistive elements. The traditional methods of testing, we have the weighed electrode method. This is where current is injected through the electrode sheet. We measure the voltage drop and calculate resistance and resistivity that way. And the 4-point probe method, we force current across the sheet, measure the voltage drop. But with both cases, we have one value of resistivity, and it's not possible to separate out the individual elements of resistivity. For instance, the composite layers and the current collector and the interface resistivity. It's not possible with the traditional electrical methods to break out those elements. The RM2610, this is the Hioki system. Similar to the 4-point probe, the probes test from the top surface of the sheet. And like the 4-point probe, we apply current and measure voltage. But instead of using 4 points, we're using 48 probe array. and we're measuring voltage distribution across surface area, very small surface area. The system requires certain input parameters or parameters that the engineer needs to know. And those are the composite layer thickness, the collector thickness, and collector resistivity. And typically collector resistivity is going to be textbook value for copper or aluminum. Now you might be wondering, well, how do we separate out those elements of resistivity? So the system uses inverse analysis, and we also use a finite volume model for the calculations. And the outputs of the system are going to be the composite resistivity and interface resistance. So the first step, this is to acquire the measured potential distribution. So this is where we apply a constant current and measure voltage over a small surface area at multiple points. And in the next slide, I'll go into some more details. But that is our observed or measured potential. So having a closer look at the probes, the probes shown in blue are used to source and sink current, and the inner 5x5 array of probes are used to measure voltage. The entire area is approximately 1 millimeter square, so it's a very, very small area, and the pins are very, very tiny. So we capture, as the first step, the measured potential distribution. The second step is the inverse problem analysis, the modeling. So we perform modeling and obtain the calculated potential. So as I mentioned before, the user has to enter the composite layer thickness, collector thickness, and collector resistivity. So using the model, the system will start with some value, initial value of composite resistance and interface resistance, and it will calculate the potential distribution based on those parameters. And then, since we've measured the potential distribution in the previous step, we can compare the calculated curve with the measured curve. And we then adjust the variable values and recalculate the potential distribution. So the process is repeated until the distribution curves, in other words, are measured and are calculated, are in close agreement. And at that point, when there's close agreement between what we've calculated and what we've measured, the parameters for the composite resistance and interface resistance are output from the system. This is on this slide, this is a brief view of the system components. So the system comprises of a press unit, which is hand activated. The test fixture that contains the probes, which make contact with the surface of the electrode sheet. There's also a temperature probe and the electrode measurement meter, the RM2611, that's part of the system. There's also a PC software, which requires a software key. Obviously, the PC is provided by the purchaser. We don't provide the PC. The entire system will fit on a normal standard workspace or a work table. So it's fairly lightweight and easy to transport. And so that is just a very top level view of the RM2610, what it does and what sets it apart from traditional methods. And with that, I'd like to pass it back to Nao-san. Thank you.
Thank you, Isan. So we work with some companies, and we found we made some experiments. And today I'm going to introduce 3 case studies. The first one is the CNT particle size versus slurry or electrosheet performance. So Joco is a manufacturer who Joco is a manufacturer of ultra high pressure homogenizer. Nanogenesis is one of their products, and we use this nanogenesis to make CNT with a different particle size. So this homogenizer applies preset pressure to materials in the system, and the flowing particles collide repeatedly until they get to the desired size. So we applied 50 megapascal, 100, 150, 200 megapascal to make CNT, different size CNT. And we prepared a slurry samples with NMP and tested those with a slurry analytical system. So this graph shows CNT slurry DCR results against the particle size. And as you can see, highest DCR was observed in the 1.0 micrometer to 2.0 micrometer particle size range. And DCR depends on the particle size, not the pressure we apply to other materials. And also, in addition to slurry evaluation, we did electrosheet evaluation as well. And RM2610 was used. And internal resistance of the electrosheet was plotted against CNT slurry DCR. So interface resistance gets smaller as DCR value increases. So according to these test results, particle size affect slurry and the electrosheet performance. It indicates that producing CNT powder with precise particle size control is critical, and also it is essential to find out the sweet spot between particle size and the performance of slurry and the electrosheets. And the second case study is dispersant quantity versus slurry's rheological and the electrical performance. We made 4 kinds of slurry samples using these materials. We changed the quantity of dispersant 4% to 8% of the conductive additive quantity. First, we made a conductive additive slurry. Then we added active materials and binders. Then all materials are mixed together. So these 4 slurry samples were tested with a slurry analytical system, and also viscoelasticity was measured. And on the left-handed graph, you can see data of our ratio on the horizontal axis, and the uniformity values on the vertical axis. And storage and loss modulus values were plotted by shear force. So looking at 4% and 5% test results, and our ratio increased from 0.05 to 0.08. So this indicates that adding dispersant reduces the agglomeration of conductive additive, and conductive networks form as conductive pathway. And looking at the higher amount of dispersant test results, so they are plotted gray dots and yellow dots. And looking at the viscoelasticity results, so G double prime and the G prime get closer. And this indicates the increase of Slurry's fluidity, meaning improvement of coating properties. And looking at our ratio uniformity results, our ratio reduced. So from this results, we assume the conductive networks are broken down by adding dispersant. So rheological and electrical measurement, both measurements are very useful, and they help people, find out the sweet spot. And lastly, I'm going to introduce a case study about the relationship between lithium-ion battery performance and the electrical indices of cathode slurry and the positive electrode sheet. So we prepared 4 kinds of cathode slurry samples under 4 different mixing conditions. We added these materials, ethylene black, PVDF, and NP, and we mixed those materials with different mixing technique. A is a planetary centrifugal mixer. B is a thin film spin type high-speed mixer. C is a planetary mixer. So after mixing materials, we added active material, then mix again, and to adjust the viscosity, NP was added. And lastly, only for sample 1, we did additional mixing. So we tested after preparation of the slurry, we created electrode sheets as well, and the slurry samples and the electrode sheet sample were tested with the slurry analytical system and our 2610. So slurry's test results, so uniformity of the slurry were plotted against our ratio, and also conductivity of electrode sheets were plotted against our ratio. So from S1 to S4, we expect the electrical pathways were more developed, and this assumption can be supported in the test results of the electrode sheet. So S4 is the most conductive sample, and this is aligned with an assumption from Slurry test results. So we found that our ratio of the Slurry directly correlates with electrode sheet conductivity. So to check if the Slurry or electrode sheet performance the same tendency if so we checked if the tendency observed in the Slurry electrical properties and the electrode sheet property can be seen also in the cells. So we created battery cells, and we tested. We did a DCIR and charge discharge tests with finished battery cells. So this is a test results, and DCIR were plotted before and after cycling, and discharge capacity values were collected in a certain number of cycling. So S1 sample 1 showed the highest DCIR and the lowest charges discharge capacity, while S4 was the lowest DCIR and the highest discharge capacity. So as I said earlier, S4 is expected to have more electrical networks, and this assumption is aligned with the results we got. So and also we saw the DCIR increase and the discharge capacity decrease after cycling. So this indicates that conductive pathways are expected to break down due to the expansion and the contraction of conducting networks during charge discharge cycles. So this is the summary of our experiments. And from S1 to S4, the internal state, the electrical pathways expected to increase progressively, and Slurries and electrode sheet performance are aligned with the assumption. So Slurry's electrical properties correlate with the finished cell performance, and this is just one example, but we think using this Slurry analytical system and using Slurry analytical system, we can see which Slurry characteristics has impact on cell performance. So, okay, this is a summary. So we discussed battery designs tailored to specific performance requirements, and it is crucial to optimize formulations and the production process to create the batteries that meet the requirements. And there are various characterization or measurement techniques available in the market, but evaluating battery components by fabrication process gets deeper insight to battery characteristics. So using those techniques, we can do that. And Slurry analytical system and the RM2610 are used for a wide range of battery R&D and production applications. And lastly, we saw the case study correlation between Slurry performance and cell performance. So cell performance can be analyzed by going back to electrical characterization of the Slurry and the electrosheets. This is my last slide in the presentation. Michael, do you have any questions?
Boy, do we have questions. But before we begin with our Q&A, I want you all to direct your attention to our webinar survey, which is available on the right of the presentation window. If you closed the survey, you can reopen the widget by clicking the icon along the bottom of your screen. Again, thanks in advance for filling out the feedback form. Your participation in the survey allows us to serve you better. And now let's get on to our Q&A. As a reminder, just type your question into the text box or click the Q&A icon at the bottom of your screen. Questions we don't have time for will be shared with our presenters who can respond to you offline. So let's get right into it. Our first question comes from Brian, who says, how is the measurement taken? Is the slurry electrified with a probe, or are these samples taken and examined in a lab environment?
Yes, I think, yeah, I can take this question. So let me go back to the slide and sorry, let's take a look. So, sorry, this is a little bit small, but we use this vial, and it has two pins, test pins, and we inject AC signals through these two pins, and to take impedance measurement.
Yeah. Okay, thanks for that. Keep the questions coming. This one comes from Antonin, who wants to know, what is the volume of slurry required for analysis?
Yeah, this system requires 1 milliliter of the slurry.
Okay, thanks so much. Keep the questions coming. The ones we don't have time for, we'll get a written response after the event, so just keep them coming. The next one comes from Mai, who asks, what type or model of impedance measurement equipment for the slurry do you use?
Yeah, so we use the IM3536 LCR meter, and to get the next plots, we use software of the slurry. So the system is controlled through a PC, and we take impedance measurement across 500 different points.
Okay, thanks for that. This one comes from Samuel, who wants to know, can water-based slurries be used in the analytical system, such as for graphite anode slurries?
Yes. So today I introduce case studies for cathode slurries, but yeah, so you can use the system for anode slurry using water.
Okay, thanks for that. And this question comes from Nadir, who wants to know, what is the smallest sample that can be measured for sheet resistivity machine? Can this unit be used for standalone coating without the current collector?
I'll address that question. So we recommend at least 1 centimeter square sheet. You can use much larger. I mean, at least 1 centimeter square. 10 centimeter square works pretty good. You can measure multiple points across the sheet. The size of the sample doesn't affect the measured values. And the system, yeah, it has to have an electrode sheet, so it's looking for that particular structure. So you can't test like a standalone, like aluminum sheet or something like that. It's very specific to electrode sheets. Thank you.
Okay, great. Quinwood says that S4 has the best, but its uniformity is low. I guess the fourth sample. How does it affect the cell performance? Anyone?
Yes, I'll take this.
Okay.
S4 is a best uniform. Yeah. So yeah, so I think the question is related to this slide, and if so, materials, conductor material. So if uniformity is high, the conductor materials disperse well. But if not, it's a agglomeration is formed in the slurry. That is a basic understanding, and so in that from that standpoint, so the some areas in the slurry has low impedance, but the other area is not. So the slurry is not uniform. So when we use the battery cells with that kind of slurry, probably there's some current is the some current is focused on a specific area. So, and if the slurry's impedance is also not uniform, if uniformity is low, so probably heat generation is seen in some area of the slurry more. Yeah.
Okay, thank you for that. Again, keep the questions coming. We'll get to as many as we can in the time we have remaining. Shiyun asks, for slurry current collector interface, can one use EIS instead of DC measurement? And what are their respective pros and cons? Are you still with me?
I'm sorry. So a slurry is a solvent solution. So it's not usually water or organic solvent are used in the slurry solution. And in the case, we can only do AC IR measurement. So that's why I believe for characterization of the slurry, AC measurement is only used.
Okay.
I hope that answer.
If you have a follow-up, just go ahead and submit it, and we'll get it to him. Ang would like to know: can I use this resistance measurement on anode metal sheets?
That's the RM2610. Yes, yeah, you can. You can use both anode and cathode.
Okay, that's all the time we have questions for today. I want to thank you all. We appreciate your time and your expertise on today's topic. It's greatly appreciated, let me tell you. Thanks to our sponsor, Hioki, as well as to everyone in the audience. We appreciate your attention and your participation to our event today, especially during the little interruption we had. Within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. Please feel free to invite your colleagues and peers who have not been available to listen to the event. And this webinar was copyright 2024 by Informa. The presentation materials are owned by or copyrighted by Informa Markets. The individual speakers are solely responsible for their content and opinions. On behalf of our guests, Now-san and Heesan, I am Michael Krieger. Thank you for your time and have a great day.